on the last lecture, we started to talk about essentially floating point formats. So, in other words, how to store the floating point number, or the number with a, if you like, decimal point or a radix, right? As we know, we can represent a number with the decimal point to the number with the radix in the binary form, right? So, okay, as we discussed before, so what we need, so of course computer stores only numbers in binary form, because as I said, so for computer it's the most foolproof strategy to store just zeros and ones, presence of voltage and absence of voltage, essentially. Okay, so let us talk about how we can store the binary number with the radix. So first of all, we need to store sign, right? Which can be plus or minus. So it means that we can encode it with just one bit of information, right? So 0 or 1. So, and this is exactly what is going on in all precisions which we will consider. Okay, next, as we know, binary number consists only of ones and zeros, right? So it means that we can agree that we will move radix multiplying by 2 to corresponding power. We will move radix to the right of the first one from the left. So essentially we will represent our binary number as 1 and remaining significant bits, right? So, and then if we agreed about that, we don't need to store this bit because we know that it's always 1, this one. Okay? So this form is called a normalized floating point number. So, and of course we have some, because we moved this radix right here, so we have multiplication by 2 to some power. Remember that in binary representation, when you multiply by 2, so you move your radix to the right. If you divide by 2, you move it to the left. So it's the same idea as with 10. If you take the decimal number and number with base 10, right? So if you divide it by 10, then it moved the decimal point to the left 1 digit, right? If you multiply it by 10, it moved the decimal point to the right 1 digit. Okay, so so we have this representation, normalized representation of the floating point number. So let me tell you that although there are different formats of representation of the floating point number, now one format is dominating just practically everywhere. So and this format will be is called IEEE. So IEEE means Institute for Electrical and Electronics Engineers 754 floating point standard. And we will consider this specific floating point representation standard. So I can tell you that I was encountering before other standards, but now they are practically, so I don't think that you will ever encounter them. So, but I mean, they're pretty close, other standards as well. So as a result, so you, if you will learn really well this IEEE 754 standard, so it will be easy for you to figure out how to work with other standards, if you will ever in your life encounter them. Okay, next. So what else we need to know? So we agreed that we need just one bit for representation of of a sign of a binary binary number with a radix, so with the floating point. So why it's floating? Because by multiplication by 2 we can move this position of the point, so this is why it's called floating. Okay, next, so we need to store this power of 2, right? And for single precision we have 8 bits to store it. So for double precision 11 bits, for long double we have 15 bits. So now the thing is that as you understand, power can be positive and negative, right? So 2 to the -2 power, for example, or 2 to the whatever 10 power. So we will talk specifically how to address this thing, how to store power with the sign later. Okay, but to store power of 2, so we are using different number of exponents. So what it gives us a range of representation of the numbers. So the smaller is the power, the smaller are the maximum and minimum number which we can represent, right? Okay. Next, the remaining is the number of bits which we can use to represent this binary number. I mean this part of the binary number, which is called mantissa, as I explained on the last lecture. So every bit takes values just 0 or 1 as usual. So, and mantissa for single precision contains 23 bit, and altogether single precision uses 32 bits for representation of the floating point number. So with in the case of double precision number, and this is the default standard for MATLAB, and most of you will use just, if we are talking about computers, most of you will use double precision. If you are talking about microcontrollers, for example, or some other embedded applications, so for example for car industry or other things, so there in many cases the default standard is single precision, because there you don't need this accuracy which gives you double precision. While for numerical computations, for scientific computations, usually you need accuracy of the double precision, and I will explain later why it's important. So double precision, so if single precision altogether, all these things, sign, exponent, and mantissa, they use 32 bits for single precision. For double precision, surprisingly, it uses 64 bits. So as I said, long double is used inside of your inside of some special floating point units, like coprocessor inside of your processor uses long double representation to compute everything with accuracy which will be more than double, and then just throw away extra digits to give exact value in the double precision, guaranteed. So, but we will talk about it a little later. So these are the two things which you need to remember. So essentially, single precision 32 bits, double precision 64 bits. Okay, next. So once again, we are considering left justified numbers, so-called left justified numbers. So when radix stays right here, right? So to the right from the first one from the left. Okay. Yeah. So this is an example. For here it is. So for example, the decimal number 9 can be represented in binary as 1001. So which means that if we are talking about this format, we can represent it as, so what does it mean that we have an integer number? It means that the radix is to the right of this number, right? So it means that we have an integer. So it's right here, the radix. So it means that we, in order to have left justified number, so which means that radix has to be to the right from the first one from the left, which means that radix is supposed to be here. This is the first one from the left, right? So we need to move it here. So we need to move it 1, 2, 3 positions, right? So it means that I'm moving radix here 3 positions, but then compensating it by multiplying by 2 to the power 3. So if you see, if I will multiply, so the radix moves here, right? So I'm getting my original number. And of course, sign is plus. So this is a representation of the number 9. Okay, could you please tell me how many bits I need to represent this number 9 in the floating point representation for this binary number? Could you please tell me? So how many bits I need to represent sign if I don't know it? So
just 1 bit for the sign.
Just 1 bit for the sign. Okay. Number 3. Number 3. So how many bits I need to represent it?
2.
2 bits, right? Because 2 bits can represent all numbers up to 4, right? But 1 bit can represent just 2 numbers, right? So from 0 to 1, right? So okay, okay. A little later you will see that this is not as simple, but let us say 2, okay? Okay, 2 here, 1 for the sign. Now, how many bits I need to represent mantissa? Mantissa means this, because we know that the first digit is 1, right, by agreement of left justified number. So because radix stays to the right from the first non-zero 1, right? So okay, how many bits I need here?
You just need 3.
3 bits, right? So 1 plus 3, 4 plus, okay, 2, really you will see that 3, so here, right? So I need at least 6 bit, right? If we are talking about decimal number 9, right? So, but here, when we are saying that we use just 2 bits here, we are essentially saying that we suppose that the power is positive. So we know it, right? So, but this is usually not true. So, and as you will see, so you need not just the bits to represent the power, but also a little bit more to represent also the sign of the power, but we will talk about it later. Okay. Now, so essentially, explanation why I'm using this book right now, just broadcasting you this book, just to avoid doing this. So we are considering double precision number. It means that here I have 52 bits of mantissa, right? So I just don't want to write all these bits to explain you what we will discuss today, okay? So, but in the book they did it already. They did this work for us, and this is why I'm using the book, broadcasting you just the book. Okay, so once again, so we will be talking mostly about double precision numbers, because this is what you will encounter if you will be doing scientific computations. Okay. 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 Next. So there is a very important concept. So which explains why we are using more and more bits of mantissa when we increase precision, single, double, long double. So you see, mostly we are spending this increased storage, right? Increasing number of bits in the mantissa. And now you will understand why it's so important. So, okay, let us consider double precision number 1. Okay, 1 is just 1, right? So it means that radix is here, right? So we don't need to move it anywhere. So this is why power 0 here, right? So, and it's positive. We have plus 1 and just zeros in the mantissa, right? Okay, perfect. Now let us have a look what is the next floating point number greater than 1. So what we need to do, we need just change the furthest bit of the mantissa, right? And this will be the next number which we can represent using our wonderful double precision in IEEE 754 standard, right? Okay, so how can I represent this number? I can represent it as 1, right? Plus, so this is position. So if we are counting, this is position -1, -2, and so on. So this is -52, right? Position, because I have 52 bits of mantissa. So 1 plus 2 to the power -52. Okay. Okay, great. So this number, by definition, so pay attention, this is a definition. So this number, or the difference between number 1 and the next number which you can represent, pay attention, it's determined, this difference, which is called machine epsilon, and denoted epsilon mash. So, so this difference is determined only by the number of bits in mantissa, right? So because 1 and the next number, they have the same power here, they have the same sign, so we don't care about this stuff, right? So the only thing which we care about, how many bits of mantissa we have, because for the next number we are changing just the next the furthest bit of mantissa which we have, right? So in double precision it's 52, right? So as a result, this is the difference between 1 and the next number. So if you will compute 2 to the power -52, so you will get 2.22, approximately 2.22 10 to the -16, right? Clear? So as later I will formulate the rule which says that the difference, the relative difference between representation of floating point numbers is no more than half of the machine epsilon. So just because of representation, it means that approximately, if we are talking about decimal representation, machine machine epsilon essentially characterizes what are two closest number which we still can distinguish, right? So 2 to the power, so the difference between them is 2 to the power negative 52 for double precision, or approximately 2 to the power 2 multiplied by 10 to the negative 16th in decimal representation. So it means, as I said, later we shall see it, that the error of representation of numbers is no more than half of this machine precision. So which means that double precision gives us the accuracy or precision of representation of numbers approximately corresponding to 10 to the minus 16, which means 16 digits approximately. So, but it's approximate. So really, in most of the cases, so we can just say that 16 digits of double representation. This is what we can believe in. So essentially, so just if you are talking only about representation, as you later will see, so on numerical algorithms, they also bring their own errors. But if you are talking just about representation of numbers, we have all numbers represented with some accuracy or precision, if you like. So for just the error of representation is no more than 10 to the power negative 16 for double precision. Okay, so we have 23 bits of mantissa, right, for single precision. So as a result, could you please tell me what will be machine epsilon for single precision?
Would it be 2 to the negative 23?
Exactly. For single precision, it's 2 to the negative 23, which is approximately 10 to the negative 7. So as a result, if you are talking about a single precision, so you will see that you can believe in approximately 7 digits of decimal representation of your number. So you see the difference, 7 digits for the single precision and 16 digits, approximately 16 digits for the double precision. So this is what mantissa is used for. So this is why we increase number of bits of the mantissa. So you could say that, okay, but for normal practical applications, 7 digits is more than enough, right? As you will see later, all numerical algorithms, they bring errors, and most of them, they bring accumulating errors. So as a result, the longer you perform your computations, the more digits you will lose just because of the representation of your number. So what is important also to understand that none of the, so for example, let us consider decimal number 9.4, like here. So representation, so this is 9, so which we considered before already, but 0.4, so it's represented as infinite binary fraction, right? So you see these things are repeating. So it means that we have the following. So first we need to move this radix to have a left justified number, right? So we need to move this radix to 3 positions to the left to have it here, right? So this is what happens. So pay attention that this is 1001, right? So it's exactly this part of the fractional binary number, right? So 1001. And this is why, because we moved it to the left, we need to compensate it by increasing power here, 2 to the power 3. This is why we have 2 to the power 3, because we moved the radix 3 positions to the left. So when we multiply by 2 to the power 3, So in order to reconstruct the number, so it will be moved 3 positions to the right, right? Okay. Now, here we have 0, 1, 1, 0 repeating, right? This period, and then it's infinitely repeating. So because you see that this period is repeating infinitely, but we can store only finite number of digits, right? So it means that the number which we will represent, our floating point representation, even using double precision, will throw away some digits, right? Which will go after the 52nd digit after radix, right? So the first 52 digits, we have bits of mantissa to store, right? But next digits, which correspond to the exact number 9.4 in decimal representation, will be lost, right? So the question is, what to do with these digits, which are going further than 52nd digit after the radix. So first approach is called chopping. So which means that we just saying that, okay, we just throw them away. We just forgetting about their existence. So we just use these digits and that's it. So the only problem, yeah, you can do this, and in some cases where you want to simplify things, so this is what you do. But not in IEEE 754 precision. Why? Because if you throw away everything what is after the 52nd digit, you have a bias. So for example, you have 0 here. So it means that you're closer to just really the number which is throwing this away, right? So which have just zeros afterwards. If the first here the first digit is 0, but if it has 1, so you're closer to the number which is or in the middle, so which has 1 here, right? So it means that if you throw this away, so if you just always throw this away, so it means that you have a bias to decrease the number. So essentially, it's biased, this protocol, in moving toward 0, right? To decreasing the number just by absolute value just a little bit. Okay. So this is what we don't want to do. So alternative method is rounding. So what is rounding? So you remember that if you consider decimal numbers, so if we want to just limit ourselves with some given precision, so many digits after decimal point, so usually we consider it like that. We are saying that if the next digit is less than 5, then we just chop everything. If the next digit is 5 or larger, then we increase the last remaining digit by 1, right? So it's standard rounding, right? For example, if you have a fractional number 1.5 and you want to round it to the integer number, right? So 1.5 is, if you round it, so will be 2, right? So it's closer, we consider it's closer to 2, right? But if we have 1.3, for example, we are saying that it's closer to 1, right? To integer number 1. So here we can do the same. We can say that, okay, if we have 1, right, then we can put 1 here. So if we have 0 in this first one, then we will put 0 here. The only problem is that if we just saying that, okay, because the only problem is that 1 is exactly in the middle between 0 and here having 0 or 1, right? So if we have 1 here. So what does it mean? It means that if we are just saying that if we have 1 here, we put 1 here, so it means that we are still a little bit, but biased. So we will be increasing numbers more often. Yes, this difference is subtle, but we don't want to consider, we don't want to leave anything for random. So essentially, we need to agree what to, so we can also use information about the next digit. So if we have exactly 1 and all zeros afterwards, right? So we are exactly in the middle, and we don't want to be biased in either direction, to decreasing the number or increasing the number. This is why we have so-called rounding to the nearest rule. So essentially it sounds like that. So in double precision, so if the first next digit after the mantissa contains 52 digits, right? So if the next digit which we need to throw away is 0, then we round down. So essentially truncate everything what is going afterwards. If the 53rd digit is 1, then we round up, adding 1 to the 52nd digit, unless all known bits to the right of the 1 are zeros. In which case 1 is added to bit 52 if and only if the bit 52 is 1. So in other words, have a look at this representation. So in this case, okay, the first bit here is 1, right? So it means that because this bit here is 0, so we round up, right? So have a look. So we changed, so pay attention that this here we had 1100, right? But because this bit is 0, is 1, and here the bit which we had, the last one, 52nd, was 0, so we round up. But if all known bits to the right of the 1 are zeros, so if here we would have all zeros, right? Then we would use information about this bit to essentially throw the coin. If you like, we are throwing the coin and deciding where we will round this number up or down. So if it's 0 here, so then we are not going up. We are just chopping it. If it's 1, so then we are adding this 1 to the last bit. Okay, so now let us try to figure out. So essentially, in approximately 50% for this case, in approximately 50% of cases, we will be rounding up, and in approximately 50% of cases, we will be rounding down. Because as I said, so we use the last bit of the mantissa, this bit, as a coin. So like we are flipping the coin, right? So if it's 0, we are rounding down. If it's 1, we are rounding up. for the number which is exactly in the middle. So as a result, we are avoiding the bias. Okay. Okay, so this is what is used in IEEE 754. So this rounding to the nearest. So, we will denote this number using rounding to the nearest rule in double precision as FL of X. So now, so let us try to figure out what will be the error in this case. So, okay, we are throwing away the tail essentially, right? Infinite tail. So pay attention that here we have 1 1 0 0, right? Exactly the same. So you can say that here you have repeating 1 1 0 0 1 1 0 0 1 1 0 0. You don't need to say that you just have 0 1 1 0. So you can just start considering a repeating tail from here, right? And then this will be the repeating tail. So okay, so we have here 1 1 0 0. And then we are throwing away 1 1 0 0 multiplied by, pay attention, by 2 to the power negative 52, because it goes after the 52nd bit of Mantis, right? Okay, so this is what we are throwing away, right? Okay. But then also don't forget about this factor, the power, right? 2 to the power 3. So really we are throwing away not these, but these multiplied by 2 to the power 3. So as a result, we can just write it in a different way a little bit. So it will be this multiplied by 2 to the negative 51 multiplied by 2 to the 3. So what we did here, we just moved the radix a little bit further here, right? So that we have the infinite binary fractional number, which we already know. We know that this is 0.4. So because have a look here, this is what we had. So where it is? Boom, 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 boom. Yeah, here it is. So this is 9, right? And this is 0.4. So we just converted these to something what we already know, because we moved radix to the left. So so we need to multiply by 2, so or decrease power by 1 here. Okay, so it's 2 to the negative 51 multiplied by 2 to the 3. So this is 0.4 multiplied by what will be here. So it's 2 to the negative 48. And so what we are doing, so we are adding. So pay attention. This is what we had, right, before rounding, but using the rounding to the nearest rule. So because we have 1 here, and after that we have just some other ones, so we need to round up. So we need to add 2 to the negative 52, right, multiplied by 2 to the 2 to the third. So 2 to the negative 52 multiplied by the power 2 to the third. So it's 2 to the negative 48 in the rounded step. Therefore, the floating point representation, so we can say that this is our exact number to the negative 9.4, sorry. So multiplied, so here are all the computations. So this is the number which we had, right? So, I mean, this is the number which we had originally, but then this is what we are chopping away. What is going further in the end of this number, and this is what we are chopping away. So we added 1 and chopped away this, right? So I explained it here. So this is 1 in the 52nd position, right, of this number 9.4, and this is what we chopped away. So if you just subtract all these, so you're getting that really the number which you've got, this one, using rounding to the nearest rule, is 9.4 plus 0.2 multiplied by 2 to the negative 49. So in other words, computer using double precision representation and the rounding to the nearest rule made so this representation contains intrinsic error, so which corresponds to this. When we store 9.4 in our computer using double precision and IEEE 754. So this is our rounding error. So what is really important, that most of the numbers which we will store, the floating point numbers, they will not be exact, those numbers which we are trying to store, because you saw that in binary representation, even if we convert such simple number as 9.4, right? So we have to lose some information because we have infinite fraction. So as a result, this is what we need to do. So we need to throw away some part, right? And round up, for example, in this case. So there will be intrinsic error of double precision representation. So we always have an error. Now, obviously, so pay attention that here we were multiplying by 2 to the power 3 all the time, right? So as you understand, if you would represent not the number 9.4, but the number 900.4, for example, so this power here would be higher, right? As a result, so the corresponding error of the representation will be higher as well. But it is higher just because the number which we are trying to represent is larger, right? So just because of that. Okay, but as you will see, the number of digits after decimal point, if we will convert it back to the decimal representation, will be the same. So, and this is why we need to introduce, pay attention please, these concepts which we are talking about right now are absolutely fundamental. You will use it during the whole course. So if we have some computed version of exact quantity x, right? Like here we have some double precision representation of exact quantity 9.4, right? For example. So then absolute error of this computed quantity is difference, absolute value of the difference between these two quantities, computed and exact. Okay, so absolute error is used in many cases. The only problem with that if you increase the quantity, usually usually your error also will increase, just because you're increasing the exact quantity as well. So this is why we can consider relative error. So why? Because we can, it's like error in this relative error is essentially the ratio of the absolute error the difference, right, divided by the value. As a result, you are getting an error which you can convert, for example, to percents of your exact quantity. Okay, so what does it mean? It means that you can say that, for example, if the relative error is 0.1, you could say that, okay, I have an error 10%, right, of the exact quantity. So in this case, we are essentially from here we can say that how many digits of the decimal representation we can believe in. So now about relative rounding error, because we use this rounding to the nearest rule, so which essentially allows us to avoid bias, almost avoid biasing to up or down, right? So our relative error cannot be more than half of the machine epsilon. Because pay attention, relative error is when we will compute the difference of these, for example, right, and the exact value, so power will stay the same. So when we compute the difference and divide by the number itself, this exact number, the power, this part multiplied by 2 to the power 3, so it will go away because it's the same for both numbers, right? So the result, this part, so the accuracy of representation is characterized by just the number of bits of mantissa, relative accuracy, what is important. So this is why we need relative error, because to get rid of influence of this part of the representation. So as a result, we will get that the difference divided by the exact number, so it will be less or equal than half of the machine precision. I told you that machine precision for double precision representation number in IEEE 754 format, so is approximately 2 to the negative 16, right? So you can use your calculator. It's 2 to the power negative 52. So 1/2 gives you approximately 10 to the negative 16, right? So it means that the relative error is less or equal than 10 to the negative 16, means approximately that 16 digits after decimal point in the decimal representation will be more or less exact, right? So if you represent your number, so here it is, for example, but pay attention that really error can be less, not necessarily 1/2 of machine epsilon. For example, in this particular case, so if you so it's the worst case scenario, this one, the equality here. So for example, in our case, so if you just calculate the relative error, you will see that it's 8/47, right? So it's approximately 1/6 multiplied on the machine epsilon, if you will compute it. So it's less than 1/2 of machine epsilon, right? So you really get an error which is 3 times less than the maximum error of representation, the relative error of representation. Okay, so let us compute the double precision representation and the routing error for just the number 0.4. Okay, 0.4, we know that this is this number, right? So we were doing this conversion before. So the result, first of all, you need to get it to the left justified form. It means that you need to move this radix, right, 2 positions to the right. So here and here, really. It's supposed to be to the right of the first one from the left of the representation of your number. Okay, so it means that 0.4 can be represented in this form, right? And then infinitely repeating part, right? multiplied by 2 to the negative 2. Why? Because we moved it to the right, so we need to compensate it by multiplying by 2 to the negative 2, which moves it to 2 positions to the left, so here. Okay, first of all, it's positive number, so it contains plus sign, okay? And here we have 1.1 and infinitely repeating numbers. But then, of course, because they are infinitely repeating, so we have some part which will be chopped away, right? Multiplied by the same power. Okay, then according to the rule, which corresponds to the rounding to the nearest, so because it's not 1 and all zeros afterwards, right? So it's not in the middle. It's a little bit closer because of this part, right? It's a little bit closer up, right, to the higher number. So we are adding 1 here, according to the rounding to the nearest rule. So adding here, so 1 plus 1 gives us 0 here and 1 here, right? Okay, so the result, this is what we will get. So this is exactly what happened after we added, right? 1 to 0, 1. If we add 1, so we are getting 2. Representation of 2 is 1, 0, right? Okay, so multiplied by this power. So it means that we added 1 to the bit 52, which caused the change in bit 51 due to carrying the binary addition. So if we analyze carefully, so what was thrown away here? So we discarded these, right? And that in the truncation and added this amount by rounding up. So this is the one which we added here. Okay, pay attention. We added 1 to the 52nd bit. This is 5 to the negative 52. But then we had this factor, right? And this is why it's multiplied by 2 to the negative 2 by rounding up. Okay, therefore, so we can compute it that our representation, so here are all the intermediate steps, is 0.4, the exact number, right, which we are trying to represent, plus this amount. So you see, in this case, absolute error is even 10 times less than machine epsilon. But if you will compute the relative error, for which we have this statement, right? This statement about relative rounding error. So if we will compute it, so we will see that this is just 1.4 multiplied by the machine epsilon, 1/4 of the machine epsilon. Why it is so? Because the number itself, 0.4, is less than 1. When we will divide it, so we have this change in the relative error. Okay, now let us talk about specific representation, how these numbers are stored in the computer. So here it is. So I mean, the idea is the same everywhere. First, we store the sign bit. Here it is, the sign bit. This is 1 bit for all the representations which we considered, right? Then we store all exponent bits. In double precision, these are 11 bits. So let me remind you. 11 bits for exponent and 52 bits for mantissa, right? Okay. So first we store exponent bits after the sign, and the remaining part are all bits of mantissa. So as I said before, so for the double precision floating point number, we need 64 bits, right? Okay, so they use here 8-byte word and so on. So word, this unit of information. So if bit is defined and byte which contains 8 bits is also defined, the word is different on different computers. So as a result, I don't use this this unit of information. So just all you need to remember that double precision number contains 60. I mean, uses 64 bits for storage. Okay. What is interesting that the sign bit is 0 for a positive number and 1 for a negative number. So this you just need to remember. The 11 bits representing the exponent. So you remember we need to represent both positive and negative exponents, right? So we are just using so-called bias. So essentially we need to do the following. So we need to take the real exponent which we need to represent. For example, it can be positive or negative number. And then we need to add to this exponent so-called exponent bias, which is equal usually. So for example, if we have 11 bits of exponent, not usually, it's always like that. If we have 11 bits of exponent, so we use 2 to the power by 1 less, right? So 10 and minus 1. So this is the bias. So then it allows us to represent exponents between negative 1022 and positive 1023, right? So pay attention, because here we have just 11 bits, right? So which means that 11 bits allows us to represent numbers, really to represent numbers from 0 to 2047, because 2 to the power 11, 2048, right? But because the maximum number of the amount of integer numbers which we can represent with 11 bits is 2048, but because it includes 0 also, so it means that 11 bits can represent only numbers from 0 to 2047. Okay, but using this thing 1023 as a bias, so we can represent only numbers from 1 so our bits would use only numbers from 1 to 2046. So you see, we are not using 0 and 2047. We will use it for some special purposes. So I will just tell you so that they are used to represent some infinite numbers and something else. So you will see it later, just in a few minutes. So, okay. So what is important that you use bias, right? Here. Pay attention that for single precision, so because some of you will be doing some embedded stuff and so on, so you will need to know about single precision. For single precision, we have 8 bits of exponent, right? So as a result, for single precision, the bias will be 2, so 8 bits, right? So it means that, as I said, 1 less power, so 2 to the power 7 minus 1. So 2 to the power 7 is 128 minus 1, 127. So it means that for single precision, for single precision, instead of 1023, you will use 1027 as exponent bias. So in order to get the number which you need to put in the 8 bits of exponent for the single precision, you need to take the power of 2, which you got in your binary representation, and add 127. So just like that. Okay, so yeah, for long double precision, you are getting, for single precision, as it says, so 127. So I explained you this already. For long double precision, it's good exercise to compute this. So why this is the bias? Okay. Now, if we consider number 1, for example, we know that in binary representation it's positive sign, right? Then left justified number 1 radix, and then zeros everywhere here, right? And 2 to the zeros power. Okay. First we store sign. We agreed that, not just agreed, so it's just according to the standard. Sign plus correspond to 0 here. Okay. So first we store the sign. Then about the power. This is power 0, right? So what we need to do in order to get the number which we need to store in the exponent bits, what we need to do with this 0? Could you tell me? Okay, we need to add exponent bias to this 0, right? 1023. What 1023 can be represented as this. Pay attention that we just store these bits of information, right? But the minor bits, so essentially the radix for the radix would be here. So 1023, these are nothing else. So pay attention. 1024, it's 10 to the 2 to the 10th power. So if we add here 1, right? So we will get here in the 10th position. So we will get 1 and zeros here. So okay. So don't forget this. So you need to add the exponent bias to the power which is here. So then we have this. Okay, and the whole mantissa afterwards consists only of zeros, right? So here are all zeros, right? Okay. Now, yeah. So here it is explained that how we store it. So, and you can just convert this number to the hexadecimal format. So, and it will give you this. Okay. Next, let us store, so consider another example. Let us store 0.7. Then it will give us, okay, so pay attention, it's positive number, right? So sign bit will be 0. So exponent is 3. So, and 52 bits of the mantissa are these. So you can try to store it. So now, what is the most important thing? You remember we said that we considering always left justified number, right? So we need to move the radix to the right of the first one from the left. could you please tell me, is there a number which we cannot represent in this form? So you see, in order to have radix to the next to the first non-vanishing one, right? So first one from the left, we need to have at least one, right, in our binary representation, one non-zero digit. But 0 doesn't contain any non-zero digits, obviously, right? So 0 is just 0. All digits of whatever number of bits of the mantissa you store doesn't matter. So it will be all these digits has to be 0, and we cannot store 0 in the left justified format. Okay, so this is exactly where these special exponent values come into play. So 2047 of the power bits. 2047 is used to represent infinity. So, but in order to store 0, we use 0 in all bits here, in all bits of exponent. So if we have 0 in all bits of exponent, so it means that we have 0 as a representation. So have a look here. So here it is. So 0 is represented in a special way, like that. Okay, next. Infinity, so okay, we store it like that. So so first of all, there can be plus or minus infinity, right? So we use sign in this case. So it's either for plus, so we will use 0 in the sign bit. For minus, we will use 1 in the sign bit. Okay, and not a number. So for example, so you see, if you divide 1 by 0, so it's considered positive infinity. If you divide -1 by 0, it's negative infinity. But if your computer cannot decide what it is, so it's not defined. So for example, 0 divided by 0, right? Or if you will try to compute square root of the negative number, it's not defined. It's not infinity or something like that. For example, if you try to compute logarithm of 0, right, of really small number, so it will give you infinity, right? But, or if you're trying to compute, let's say, tangent, right, of 0, no, not 0, tangent of pi by 2. So sine, tangent is sine over cosine. Sine of pi by 2 is 1, right? Cosine of pi by 2 is 0. So it means that computer will use this. So it will give you that this is positive infinity. If you will try to compute tangent of negative pi by 2, so sine of negative pi by 2 is -1, cosine is still 0, so it will give you negative infinity. But if you will try to compute something, result of which is not defined, the computer will give you none, or in other words, not a number. So, and not a number will essentially contain all ones in the first 3 bytes. So it means that sine will be 1, and all these will contain ones as well. So essentially, if you have all ones in the first bytes, so as a result, it is not a number. Okay. Now, if you want to represent 0, so in machine representation, it will have all zeros, just all zeros. But also we can use, so have a look, if we use special exponent 0, right? So we can also use the remaining bits to represent very small by absolute value non-normalized floating point numbers. So essentially, we are saying that we will use 0 here. So pay attention, it's not normalized, right? It doesn't have 1. So if we have power, just all the exponents which are equal to 0, like that, all the exponent bits here which are equal to 0. So then we are saying that in such a case we consider numbers which contain which can be represented as 0 point, then all the bits of the mantissa multiplied by the special power negative 2 to the power negative 1022. So pay attention that in this case this power is defined. So if all exponent bits are zeros, we use special power for the 2, and it allows us to include the numbers, so which are so-called subnormal floating point numbers, because we are not using left justified. So instead of 1, we have 0 here, but we have predefined power here. Okay. This range allows us to extend our the smallest numbers which we can represent by few more orders of magnitude. So the smallest, this is why the smallest number which we can represent using double precision is this one. So this is the representation. So essentially, pay attention. Okay, sign can be plus or minus, doesn't matter. So here, the exponent all zeros, so which means that we are saying that we use this particular representation, right? So, and here we have our bits of the representation, and we remember that they are multiplied by 2 to the predefined power. So altogether, this will give us, pay attention, 2 to the power negative 1022, right? But this is 52nd bit after the radix. So you need to add here, so you need to multiply this power by 2 to the negative 52, right? So altogether it will give you 2 to the power negative 1074. So this is the smallest non-zero number which you can represent, I mean, by absolute value, which you can represent using double precision format. So pay attention that machine epsilon doesn't mean that you cannot represent the numbers which are smaller than these. You can. The only thing is that, but you cannot represent numbers by absolute value less than this number. So this is the smallest number by absolute value. So why you can represent numbers which are smaller than machine epsilon? Because you can use the power, right? So negative power here, no problem. Okay, and of course, 0 is a special number. It will contain all zeros everywhere, including the last digit of the mantissa. So this is why, for example, if you want, so if you're writing, let's say in C or and you want to just create array of zeros, you can tell your computer to put 0 everywhere in all bytes of your memory. So this is usually done using the memset command. So which is extremely optimized, so using assembly language inside and so on and so on. So essentially, 0 is conveniently represented in floating point representation according to the IEEE 754 by all zeros in all bits of your number. Okay, I will stop here. And we will continue on the next lecture.